For this next set of slides, we're going to be focusing again on linear regression, how it relates to Pearson correlation, and I think we'll have time to actually get a little bit into what's called multivariable regression. A lot of this relates back to that basic Pearson correlation concept that you've heard about earlier in the previous videos. So we're going to focus a good bit here also on this thing called the R-square value, and we'll go from there. So on the last video before this one, we had all this output from this command, regress, life expect 14, household income. We got all this stuff, and I briefly introduced you to what this stuff was. We spoke a little bit on this. We're going to come back to this here in a second. I just want you to see, what this output tells us. But before we go there, I want to tell you that when we did that linear regression, a lot of people might refer to that as a linear regression model. So this is actually our model, and this is a simple model because it only has one predictor. Life expectancy, our Y variables, our outcome, and then household income in this case is our only X variable or only predictor. So the model has an outcome in a linear regression model. This is all called a model. This command, people actually call that a model. So it has one outcome, life expectancy 14 in the case of the one we just did. It has one predictor, which is household income from our previous video and what we'll also cover here in a second. Since it only has one predictor, we'll call this a simple linear regression model. It's not multivariable, it's just simple. If we had more than one predictor, say like beyond income, something like smoking, then the model would be multivariable. And we would just type in regress, life expect 14, household income, and then we can keep adding X variables. So we could put the smoking variable right here and then hit enter and it'll work. Now, we need to understand real quick again what the output means. So we have this output up here and we have all this output here. What does all this mean? So the output up here that was in this top right corner gives us the number of observations. It gives us the p-value for the entire model. Now if you only have one variable like household income and it's significant and this is the p-value, then the p-value for the whole model will also be pretty similar, if not the exactly similar. I'm not for sure, if the software computes the p-value a little differently between here and there, but it's usually pretty similar. This is referring to the p-value from a t-distribution. For the model, it's doing using an f-distribution, which is a different distribution that we haven't talked about yet, and we're not going to in this course, but you can see that the p-value for this f-test is less than 0.0001. So it is a statistically significant model, and the p-value for household income is less than 0.0001, which is definitely a statistically significant predictor for life expectancy. So in that top right corner of that previous output, this stuff up here, we see that the number of observations that we had complete data on were 3,134. The model p-value is there. And then we also have this thing called the R-squared and adjusted R-squared. That's what the ADJ is, adjusted R-squared. And this is the percentage of variability in our outcome, life expectancy, explained by all of the model's X values. In this case, only explained by the one variable, which was household income. So you could actually say household income explains 42% of the life expectancy data we've got for the United States. It explains 42% of the variability in life expectancy. Now, these R-square values can change as you add more variables or take them away. So where does that R-square value come from? So do you remember R from the Pearson correlation? Not Spearman's rho, but we're talking about when you do Pearson correlation for normally distributed data. Well, the r square is the same r, but we're just squaring it. So if it's a simple linear regression, just one variable, that r is going to be the same thing that we use to calculate the r square. And the software does it all for us. So you'll also see adjusted r square, which is really similar to the original r square, but it takes into account the number of predictors used. So when you've got multivariable models, you kind of get reductions in your original r square because it's punishing the r square for having more predictors and smaller sample size. So large sample sizes with few predictors will not have an r square that's adjusted. That's much different than the regular r square. But if you have a lot of predictors, especially insignificant predictors, and a low sample size, your adjusted r square can be quite different from your regular r square. The adjusted r square will always be less than the r square. So again, for a single predictor, like a simple linear model, the adjusted r square will be almost identical, if not exactly the same as the regular r square. If you need to visualize that, we'll do an example. So when you do your simple linear regression model, life expectancy 14 and household income, it gives us this r square value. This r square value is based upon this single predictor household income. We also see our coefficient here, our y-intercept coefficient, our beta value. So this is all y equals mx plus b. Remember that, the line. So we have the r square of 0.4207. Remember Pearson correlation? We could do it two different ways. We could do the pairwise Pearson correlation with the significance, and we can see that the household income is correlated with life expectancy. It's statistically significant, and the R value, the Pearson's R value, is 0.6486. If you want to do the command the other way, just correlation, it doesn't give us the p-value. We can still see the exact same R value for Pearson, 0.6486. See it there? See it there? 0.6486. Now, what did we say about the R square value in linear regression? The R square value is the R value, 0.6486, squared. So 0.6486 times 0.6486. So if we were to actually do the calculation, so in Stata you can type in display and then type it in 0.6486 times 0.6486, and it gives us 0.42068. See that? 0.42068, 0.42068, 0.42068. You see that? It rounds right there. It is. It's right there. So that's where that R square comes from. It really relates a lot with like that Pearson correlation. So you can imagine that linear regression then tends to assume that you've got normally distributed data going into it. And we'll talk about that later on in the next video about how to deal with that. So another thing that we need to go on to is letting you know that the world isn't y equals mx plus b. There's a lot of other dimensions or other variables that may impact your outcome. So we know life expectancy isn't only influenced by income. It might be influenced by diet or by human behaviors. Diet and human behaviors are somewhat related to income, but there are other things that are not related to income. So the world's complicated. So maybe we want to see if other factors like smoking are predictive of the average county life expectancy for the United States. Maybe we want to see if we can do a better job increasing our R square and understanding more about the variability in life expectancy, better predicting what factors influence it and how we can maybe address it. And again, the world is complicated, so there are many possible predictors that you might be interested in, and there might be confounding variables. So how do we deal with that? It's really simple, actually. So remember our earlier command, regress life expectancy 14 household income? Well, now we're going to add another x variable. So this is our x2 variable. This is x1, we got an x2. You can mix the order of your x's up and you'll still get the same coefficients. They'll just appear differently here in the order. So you put your command in there. Then we see our R square. It went from 0.42, now it's up to 0.47. and the adjusted and the regular R-square are not all too different, meaning that this is contributing a lot to the model. So we see that our overall model is statistically significant. And we also see that both of our predictors are statistically significant. We really don't care about the p-value for our coefficient. This can be high, it can be low, it really doesn't matter. I'd rather it not even be there. And we're not going to focus too much on the confidence intervals for this class on that. We can really make this model more complicated and add a bunch of things. And I put one on here just because I want you to see that not everything that goes into the model is significant. So now I've added, for predicting life expectancy, household income, current smoking, auto mortality rate, rural, like whether or not it was, I have to check that variable if it was percent rural. What percentage of the county is rural or not? It may have been a yes/no variable, 1 or 0. Diabetes percentage, and then female percentage. And we see income statistically significant, smoking significant, auto mortality rate significant, rural significant, diabetic percentage significant. Percentage of the county population that is female, and this could be the other way around, the percentage that's male, it's not significant. The p-value is 0.725. Overall, though, even with all of this stuff in here, even though this isn't significant, the overall model is significant. See this? This is the p-value for the overall model. So the model, the whole thing, is statistically significant, but it's still not our best model or our most parsimonious. The word parsimonious means the simplest explanation. So you would cut out this stuff. You'd cut out this 0.725. We only want to see statistically significant variables or ones that are very close to achieving statistical significance at the 0.05 level. We see that this model explains 65.9% of the variability in life expectancy, much better than 42%. And we can also read into these coefficients as well. We see that this coefficient here, household income, is positive as income goes up, life expectancy goes up. As smoking goes up, life expectancy goes down. As the auto mortality rate in the county goes up, life expectancy goes down, as you would expect. If it's rural, then the life expectancy goes up. If it's more urban, life expectancy goes down. If it's diabetic, more diabetes, lower life expectancy. Female, more female, well, it's really irrelevant. So more or less, it doesn't matter. This coefficient we don't care about. It's not significant. We're not going to keep it. So we get all this information here. This is the stuff that was in that top right box. So again, p-value for the whole model is statistically significant. This is less than 0.05. And the whole model explains 65.8%. You can round up. The adjusted R-square is a better one to use. We really don't care about the constant here. And again, this isn't statistically significant, so we can drop it and we can run the model again. So there's our simple model at 47% with household income and just smoking. When we put them all in there and we drop the female one, we see that we're still at 66%, 65.83 on the regular R-square, adjusted 64.8%. So this model is explaining a lot about life expectancy. It's not apparent to us, though, which one's the most important or anything like that. But you can see which things are associated with improving life expectancy, as well as which things are inversely associated, like smoking, auto mortality, and diabetes. Being rural and having more money, those things help life expectancy. And you could actually plug in your own values if you wanted to. There's an equation here, so usually y equals mx plus b. Well, here the formula is y equals m1x1 plus m2x2. If you want to see an example, this would be your household income coefficient. This is your smoking coefficient, the negative 0.044. M3 we could put in negative 0.059. M4 we could put in our rural variable, and that pretty much wraps this part up. So